Okay, let us start. I cannot wait. Let us to go back from where we stopped last time in section 17.6. In previous class, we already discussed what the meaning exponential of a complex number z, where ez is equal e to the power x times cosine plus I times sine, which is this one here. We had some examples. Also, we discussed how we can derive the exponential e to the power ez is equal e to the power z itself, and the properties which is nearly the same as of the real number. Also, we studied the definition of logarithm in logarithmic of complex numbers. We have two logarithms. I mean, the small ln of z, which is equal logarithm of absolute z with base e plus I times the small argument. But the small argument is equal theta plus 2 and pi, where n is equal positive, negative, 1, 2, 3, and 0, which goes, I mean, the integers. Also, we had some examples regarding the ln. Then we defined the properties of ln, which is the same as the properties of real numbers. I mean natural logarithm. Now the principal value of complex, which has the capital L, is equal ln of absolute z with base e plus I times the principal argument of z. But the principal argument is the angle theta between minus pi over 2 to pi. Pi included, minus pi is not included. Also, we had some examples, and we will stop here at the definition of complex powers. If C is any complex number and Z is not equal 0, then the complex power Z to the power C, I mean complex number to the power of complex number, is defined to be Z to the power C is equal e to the power C times ln of z, e to the power c times ln of z. But here ln is a small ln, so it will be a multiple value, which is equal here e to the power c times logarithm absolute z with base e plus I phi theta plus 2 and pi, which is the small argument, where n is equal 0 minus plus 1 minus plus 2 and so on. So in general here, for example, if I said that z to the power 2i, this means is equal e to the power 2i times ln of z. We will see examples now, inshallah. Now, if we replace ln z by the principal logarithm, which is the capital N, so that becomes e to the power c times the principal logarithm of z, which is called the principal value of the power z to the power c. الآن خلينا نشوف some examples. Let us to see the examples, how we can apply to the complex power. بيقول لي find I to the power 2i, part A. How we can find I to the power 2i. هلا I to the power 2i, it will be equal e to the power 2i في ln I, which is equal e to the power 2i times logarithm absolute I with base e plus I في الargument of I. The complex number I is located here, so it is pi over 2, the theta, which is here equal e to the power 2i times the absolute value of I is equal 1, logarithm of 1 with base e plus I times theta pi 2 plus 2 and pi, and that can be simplified. هلا logarithm 1 with base e is equal 0, equal to the power e to I times I times half pi 2 plus 2 n pi, n is equal 0 minus a plus 1 and so on. This can be simplified more to be I times I, which is I square minus 1 e to the power minus 2 times pi times half plus 2n, or n is equal 0 minus a plus 1 minus a plus 2 and so on. It's just a matter of calculation. It's not very hard. Any question for this example? طيب نشوف part B. Part B. I need minus 1 to the power 2i. This is equal e to the power 2i times ln of minus 1. Well, that's equal e to the power 2i times logarithm absolute minus 1 with base e plus I. What's the argument of minus 1? It is pi plus 2n pi, and that becomes e to the power 2i times absolute of minus 1, it is 1, logarithm 1 is 0, plus I pi times 1 plus 2n. I times I, which is I square, is equal minus 1. So that's equal e to the power minus 2 pi times 1 plus n, 2n, sorry. Not n. 2n, and the value of n is equal 0 minus a plus 1 minus a plus 2 and so on.
Professor, can you please repeat how we got rid of the I in the last line?
How we got? Okay. Absolute of minus 1. I, here, I times I is I square, which is minus 1, times 2 pi, it is minus 2 pi, times 1 plus 2n.
Okay, thank you so much. Thank you so much, sir.
Thanks. Part C. I need 1 plus I to the power 1 plus I. That's equal e to the power 1 plus I times ln 1 plus I, which is equal e to the power 1 plus I times logarithm absolute 1 plus I with base e. هلا ال 1 plus I, what's it is argument? It is pi over 4. I في pi over 4 plus 2n pi. And that becomes e to the power 1 plus I times. هلا the absolute value for 1 plus I, it is a square root of 2. So it becomes logarithm square root of 2 with base e plus I times pi over 4 plus 2n pi. Right. Now we need more simplification. Enter 1 plus I to this big brackets, so that becomes e to the power log square root of 2 with base e plus I times pi over 4 plus 2n pi. هلا I times times the big brackets again plus I في logarithm square root of 2 with the base e. I times I, which is I square minus 1 minus pi over 4 plus 2 and pi. Okay, so the big brackets here, all of these inside the red big brackets are as a power. But now I can simplify it more. بقدر أعملها تبسيط أكثر. واللي هي this is equal e to the power logarithm square root of 2 with base e times e to the power I of pi over 4 plus 2 and pi times e to the power I of logarithm square root of 2 with base e times e to the power minus pi over 4 plus 2 and pi. هلا this part here e with logarithm with base e that will be cancelled, so that's equal square root of 2. They are nearly square root of 2. الآن e to the power I في pi over 4 plus 2 and pi also is equal e to the power I في pi over 4 times e to the power I في 2 and pi times e to the power logarithm e with base square root of e. What does this e equal? How much is this equal? شو بيعطيني هون؟ مين يقول لي هون شو بيعطيني؟
I root 2.
Sorry?
Will it be equal to I root 2?
I square root of 2 or square root of 2 to the power I. To the power I. Why? Because this I will go to power of a square root. So you will be e to the power logarithm e with square root to the power I. So that becomes square root to the power I times here e to the power minus pi في 1 by 4 plus 2n pi. I took 2n, sorry. I took pi as a common factor outside. طيب الآن خلينا نشوف. This is, we can simplify it more actually. E to the power I times 2n pi is equal what? This one here. This is equal 1. How it is equal 1? How it is equal 1? مين يقول لي كيف تساوي 1؟ It is equal cosine of 2 and pi plus I في sine 2 and pi. Sine 2 and pi is equal 0. Cosine 2 and pi is equal 1. So this becomes the square root of 2 e to the power I, and e to the power I for logarithm, take I as a common factor, becomes e to the power I of pi over 4 plus logarithm square root of 2 with base e, and times e to the power minus pi of 1 by 4 plus 2n. الآن this value here, this is equal to square root of 2. This value here is equal what? This is equal cosine of pi over 4 plus logarithm square root of 2 with base e plus I في sine pi over 4 plus logarithm square root 2 of e, and this is times e to the power minus pi في 1 على 4 زائد 2n. where the value of n is equal 0 minus plus 1 minus plus 2 and so on. Is it clear? So I mean here in this example we have to simplify to the last step. Now what about if I ask you the principal argument, the principal value about here? The principal value of minus 1 to the power 2i is equal what? Is equal to the power minus 2 pi, because n, it will be 0 for the principal value. So because we will take here just only pi, we will not take 2 and pi. That for the first one, the principal value for the first one of I to the power 2i I to the power 2i, it is, when we take n is equal 0 here, it will be minus pi over 2 divided by 2, which is e to the power minus pi only. What about the principal value or the last one? One plus I to the power 1 plus I is the whole value without n is equal to square root of 2 times cosine pi over 4 plus logarithm square root of 2 with e I phi sine pi over 4 plus times e to the power minus pi by 4 only. We'll take n is equal 0. Is it clear how you can apply the power over complex numbers? Type. This finish is already done. This section is already done. So we have to go now to the next section, which is the trig and hyperbolic functions. Also here is just a matter of calculation. But you have to know how you can use these calculations or the formulas. Type. الآن, of course, the formula sheet will be provided for this section. The formula sheet will be provided for this section. So that means that we have to find. I will provide you the formula sheet which contains the necessary information for the exam. Here we will understand what's the definition and properties of trig and hyperbolic functions for complex numbers, and solving some trig and hyperbolic equations. Okay. الآن, just to remind you that if x is a real number, then e to the power ix, it becomes cosine x plus I phi sine x. Will e to the power minus x minus ix, it becomes cosine x minus I phi sine x. Now have a look here. if we added ex, e to the power ix, plus e to the power minus ix is equal to cosine x, because I sine plus minus I sine, it becomes 0, which implies that cosine x as a real number is equal e to the power ix plus e minus ix divided by 2. Of course, x here is real number. Now let us to create another equation for the sine. But if you notice that eix minus e minus ix, it becomes cosine plus minus cosine, which is 0. I sine plus I sine بعطينا 2I sine x. Therefore, sine x, it becomes e to the power ix minus e minus ix divided by 2I. Again, x here is real number. X is a real number. I need those two equations now for the next parts, which is already, I put it here that ex is equal cosine plus I sine, which is, I just proved it 2 minutes ago. If you make addition subtraction, you will get a formula for sine x, where x here just to make sure it is real number, and cosine x. Now in the same fashion, we can define the sign of complex number z, not a real, and the cosine. So if we have z is a complex number, not a real number, similarly we can define sine z to be e to the power iz minus e to the power minus iz divided by 2I. And cosine of z is equal e to the power iz plus e to the power minus iz divided by 2, which is the same procedure of defining sine cosine in real numbers with respect to the complex exponent e to the power I. Now, because we know the sine and cosine of a complex number, similarly I can define tan, which is sine by cosine, cotan, cosine by sine, secant 1 by cosine, or cosecant 1 by sine. الآن الfunction of sine and cosine defined at the set of all real number. I mean, it is analytic on the set in the complex field and وبالتالي entire. إذا هذول functions are analytic on the complex number, which is equal entire on the complex number C. Both of these functions, I mean sine or cosine. طيب tan defined where? The tan will cotan defined where? Domain tan tan analytic on will be analytic on the complex number except the complex number z, which is cosine of z is equal 0. Hello, when the cosine will be 0? Cosine will be 0 at pi over 2 plus n pi, n is equal 0 plus minus 1 and so on. طب الكوتان analytic where؟ هلا كوتان analytic on the complex number C, I mean the whole field, except where is the sign is equal Z? Sine of 0, 0, sine of pi 0, sine 2 pi, 3 pi, 4 pi, and so on. This is at n pi, where n is equal 0, minus, plus 1, and so on. Cosecant also analytic in the same domain of analytic of cotan, with secant analytic in the same domain where the tan analytic is, because you have the same cosine for the tan, and the cosecant, it has the sine at the denominator. طيب, إذن the definition of sine and cosine is already now with me, so I can define tan, cotan, cosecant, secant. الآن, let us to recall that the definition of hyperbolic functions from calculus. We said that essential x is equal ex minus e minus x divided by 2, and cosh, it will be ex plus e minus x divided by 2. الآن, we will define the same sinh and cosh for complex number as sinh z is equal ez minus e minus z divided by 2. Cosh is equal e to the power z plus e minus z divided by 2. Similarly, now you can define tanh, coth, secant hyperbolic, and cosecant hyperbolic functions. الآن sinh and cosh of z are entire functions. Are entire functions. طيب, نشوف الآن بعض identities and to see what's the difference with the identities of calculus. This is the most familiar identities for trig functions. الآن, sine minus z is equal minus z. We have the same thing with calculus. Or cosine minus z, I mean z is a complex number. Complex number here. z بتساوي x plus iy. Complex number. Cosine z square plus sine z square is equal 1. The same identities of sine z1, z2, which is the same. All of them are the same. Yes, all these identities will be given. الآن, also the identities of z, of hyperbolic. Here also z is equal x plus iy. Sinh minus z is equal minus sinh z. We have it the same in calculus. Cosh, it's the same. Cosh square minus sinh square is equal 1. All the others are the same. All these identities are the same of the hyperbolic functions. Except here sinh of z plus 2i is equal sinh z. Cosh z plus 2i is equal cosh z. This is periodic with 2 pi I. الآن, what's the relation between hyperbolic and the trig functions in complex? هلا essential iz is equal I في sin z. How? Go back here to the definition of sinh. to the definition of sinh. Here at the definition of sinh, replace z by iz. You will get eiz minus e minus iz by 2, which is exactly the same as sine, but not divide by I. So multiplied I sine by I, you will get 2. So you will get it here. Since iz is equal I في sine z. Type cos iz, it's equal cos because there is no cosine z. There is no I multiplied by the denominator of cosine. طب sin iz is equal I في sin. Cosine iz is equal cos z. So this is another way to define cos, which is cosine iz. Another way to define sin, which is sine iz divided by I. طيب الآن this is the imaginary and real part of this sine, cosine, sin, cos. Sine z is equal sine x cos y plus I في cos x cosine x sin y. How? Let us to see how number A you get it. هلا sine of z is equal sine of x plus iy. هلا according to the identity of sine, this is equal sine x cosine iy plus cosine x في sine iy, which is equal sine x. هلا cosine iy, what does this? It is cos y, صح? Cosine iy here from this identity here is equal cos y plus cosine x sine iy sine I z is equal I في sin y times I sin y, which is here equal sine x cos y plus I cosine x sin y. So this is the real part and this is the imaginary part, which is this one here, and all the others I can derive them is the same in the same procedure. Now let us to see some examples. خلينا نشوف بعض الأمثلة. يقول لي evaluate the value of sine 2 plus I. To evaluate sine 2 plus I, use the identity that sine of z, which is sine of x plus iy, we just prove it here, or part A from the previous one, is equal sine x cos y plus I cosine x sin y. Therefore, sine of 2 plus I is equal sine of 2 cos 1 plus I cosine 2 essential 1. And you just use the calculator to find it. Use the calculator to find it, but make sure your calculator is in radian mode. In radian mode. هلا part B, cosine pi minus 2i. How I find it? This is the cosine identity. هيها cosine x cos y minus I في essential x essential y. هلا cosine of z is equal cosine x plus iy, which is cosine x cos y minus I sin x essential y. Therefore, cosine of pi minus 2i cosine pi cos minus 2 minus I في sin pi sin minus 2. Cosine of pi is equal minus 1 في cos minus 2. Sin pi 0 times anything 0, which is here equal minus cos minus 2. Any question up to now? All right. خلينا نشوف الآن next example. Next example بيقول لي بده كوش الباي I. Use the identity which is cos z according to the previous identity is equal cos x plus iy is equal cos x cosine y I في essential x sin y. إذن الآن cos pi I is equal cos is 0 cosine pi plus I في sin is 0 sin pi. هلا cos 0 is equal 1 و cosine pi is equal minus 1. Sin 0 0 sin pi 0. So is this one is equal 1 times minus 1, which is minus 1. Part B. I need sin 2 pi I. According to the identity of sin, this is equal what? Sin of 0 cosine minus 2 pi plus I في cos x, which is 0 sin y, which is 2 pi sin 0 0 times cosine minus 2 pi طبعا 0 plus cos 0 1 sin 2 pi. How much is sin 2 pi? it is 0. So it's equal 0. Any question up to now؟ في أي أسئلة لحد الآن؟ الآن الموديولز sin x module sin x square is equal sin square plus sin square. Modules cosine square is equal cosine square plus sin square. Module sin z square is equal sin square plus sin square. Modules cos square is equal sin square plus cosine square. طيب. الآن, let us discuss this one in details. We just have 1 or 2 ideas left over. Sin z is equal 0 when the sin z is equal 0. When z is equal n pi. I mean, when z is equal, when n is equal 0, that means z is equal 0. When n is equal 1, it becomes pi, 2 pi, 3 pi, this is pi, 2 pi, 3 pi, or minus pi, minus 2 pi, and so on. هلا cos z will be 0 when z is equal pi over 2 plus n pi. Pi over 2 plus n pi. If you take different values of n, when n is equal 0, it becomes pi over 2. N is equal 1, pi over 2 plus pi, which is 3 pi over 2, and so on. Since z, it will be 0 when z is equal n pi I, where n is equal 0 minus plus 1 minus plus 2, and so on. Cos z is equal 0 when z is equal pi over 2 plus n pi times I, of course. Hello, what's the difference between zeros of sine and zeros of sinh? Zeros of sine has no I. Zeros of sinh, it has I, which is the same value, n pi I and n pi. The difference between the zeros of cosine z, pi over 2 plus n pi, will cos pi over 2 plus n pi, all of them multiplied by I. الآن بالنسبة للدريفاتيفز. The derivative of sinh is equal sine, z is equal cosine z. Derivative of cosine is equal minus z, which is the same derivative of calculus. The derivative of sinh is equal cos, derivative of cos is equal sinh. And how we derive those? For example, when we say that d by d z of sine z is equal d by dz of 1 by 2i times e to the power iz minus e minus iz, because this is the derivative of sine z, and that becomes 1 pi by 2i times, what's the derivative of e to the power iz? Is I e to the power iz minus derivative of e to the power minus iz بصير عندي minus بصير plus I e to the power minus iz. الآن take I as a common factor, becomes معنا I divided by 2i times e to the power iz minus iz. I by I بيروح معنا بصير معنا half times e to the power iz plus E minus IZ, which is here is equal what? It is equal cosine Z, which is the definition of cosine Z. طيب خلينا نشوف ال other derivatives. Then we will have examples إن شاء الله. A derivative of tan Z is equal what? Secant square. Here tan Z هي عبارة عن sin Z على cosine Z. You just derive the quotient rule. Derivative of cotan Z is equal minus cosecant square. Derivative of secant tan. The cosecant minus cosecant, which is all of them are the same calculus. Tan secant square hyperbolic. Cotan hyperbolic minus cosecant square hyperbolic. Secant hyperbolic minus secant tan. This is the only difference between real and the complex. Here in complex we have negative. No. Okay, in real we have the same. In real hyperbolic, I mean here. I mean real hyperbolic, we have the same. Divided by cosecant hyperbolic, it is minus cosecant cotan hyperbolic. خلينا نشوف some examples الآن. Okay. After we take the inverse, then we will discuss the examples. طيب الآن الساين and cosine, sinh and cos, all of these functions are periodic functions. الآن when we would like to create an inverse function, these functions do not possess inverse that are function in the strictest interpretation of that word. I mean, the inverse for those functions will be exactly multiple valued functions. Why multiple valued functions? Because sine of Z, it is defined by exponential here for the complex. الآن to find the inverse for these functions, it's a matter of just a very simple calculation, which is not required from you. You will assume this is equal W, then Z is equal sine inverse of W. It's just a matter of solving this equation as with respect to Z. When you solve this equation with respect to Z only, you will see that you need to take ln, and the ln is a multiple valued function. So sine inverse of Z is equal minus I ln of IZ plus 1 minus Z square square roots. Cosine Z inverse, cosine inverse Z minus I ln Z plus I, if you want, minus Z square, all of them square roots. I mean 1 minus Z square is the square root. It has the square root only. tan inverse of z, I by 2 ln iz divided by I minus z. The same, sinh inverse. Ln of z plus z square plus 1, all of them square root. Because at the definition of sinh z and cos z, there is no I multiplied by the denominator. So you will not see here. The I is only just at the sine inverse and cosine inverse. I mean, which comes from this I in case of sine. Cos inverse of z is equal ln of z plus z square minus 1. With tan half of ln 1 plus z divided by 1 minus z. طيب خلينا نشوف الآن some equations. He said solve the following equations. Sine z is equal square root of 5. That means z is equal sine inverse the square root of 5. الآن use this identity for sine inverse z. Sine inverse of z is equal minus I times ln of iz plus 1 minus z square to the power half, which is equal minus I fill in of I times the square root of 5 minus or plus, because we have different values, the square root of 1 minus square root of 5 square and that's equal minus I fill in of I square root of 5 minus a plus square root of 5 square is 5. 1 minus 5, it is minus 4, which is equal minus I fill in of I times the square root of 5 minus a plus على square root of minus 4, it is 2I. Take an I as a common factor, becomes minus I, and keep it inside the ln. Square root of 5 minus a plus 2 times I. الآن square root of 5 plus 2 positive, square root of 5 minus 2 also positive value. Now I need to use the definition of ln, which we had it today. That becomes minus I times logarithm absolute of square root of 5 minus a plus 2I with base e plus I fill argument of square root of 5 minus a plus 2 times I. So this value here always positive. So the argument for this number is equal what? It will be somewhere here. Well, argument is equal pi over 2. So that becomes minus I times logarithm. The modulus for this one is equal square root of 5 minus a plus 2 with base e plus I times pi over 2 plus 2 and pi and enter minus I becomes minus I logarithm square root 2 minus plus 2 with base E. الآن minus I times I في I square which is minus 1 وعندنا negative that becomes positive 1 times pi over 2 plus 2 and pi where n is equal 0 positive negative 1 positive negative 2 and so on. What I mean in this example that when you find out any sine inverse, cosine inverse, tan inverse, whatever, you have to continue solving with respect to ln because you know the definition of ln.
Doctor,
Yes.
do I have to memorize those functions or we will have a formula sheet of them?
We will have a formula sheet inshallah. طيب. Let us to do the last example in this chapter. We have to solve cosh z is equal minus 1. When we say that cosh z is equal minus 1, that means z is equal cosh inverse minus 1. But we know that cosh inverse of any complex z is equal ln of z minus a plus z square minus 1 to the power half. So cosh inverse of minus 1 is equal ln of minus 1 minus a plus minus 1 square minus 1 to the power half. Minus 1 square is equal 1, minus 1 it is 0, square root of 0, 0. So this is becomes ln of minus 1. Ln of minus 1 is equal what? Logarithm absolute minus 1 with base E plus I في الargument of minus 1. That becomes logarithm of 1 with base E plus I. The minus 1 it is argument pi plus 2 and pi and that's how 0 minus a plus 1 and so on. Which is logarithm 1 with base E is equal 0. So that's pi زائد I times pi plus 2 and pi, which is I pi times 1 plus 2n, where n is equal 0 minus plus 1 and so on. أجيت clear this example واضح المثال هذا. It's just a straightforward application.
Doctor,
Yes.
can we get back to the last example? Yes, this one. Yes, the last step. What is the I?
What's that?
The I mean. Yeah.
I don't understand your question. What's the
I? Where it's gone?
This one here?
Yes, yes.
I times I square, which is minus 1, times negative here becomes positive 1.
Oh, okay, okay. And now
because we have at the big brackets here, we have I multiplied outside.
Okay.
Okay, let us do one more example, and that's enough for this chapter. If I say that solve tan of z is equal 1, this implies z is equal tan inverse of 1. Now, what's the equation for tan inverse? Go back here. This is the equation for tan inverse of complex number. I divided by 2 times ln I plus z على I minus z. So tan inverse of 1 is equal I divided by 2 ln of I plus 1 على I minus 1. Now we need to calculate this one. How? We need to multiply I plus 1 divided by I minus 1 by the identity of by the conjugate. First of all, have a look. شوفوا هون. I plus I minus 1 هذا بدها تساوي I divide by 2 ln of 1 plus I minus 1 plus I multiplied by the conjugate I by 2 ln times 1 plus I على minus 1 plus I times minus 1 minus I minus 1 minus I. So when you find the multiplication by the conjugate here and side ln, so that becomes I plus divided by 2 times ln of minus I. وهذا بدي يساوي I divide by 2 times logarithm absolute minus I with base E plus I في الارجمنت لماينس I. What's the argument of minus I? Minus pi over 2. هذا بصير pi over 2 I by 2 times logarithm of 1 with the base E I times minus pi by 2 plus 2n pi, where n 0 minus plus 1 and so on. هذا بده يساوي I by 2 times logarithm of 1 0 الآن I times minus pi over 2 plus 2n pi. I في I, it is I square which is minus 1. So minus half times minus pi over 2 plus 2n pi. And just simplify this one, which is pi over 4 minus n pi, where n is equal 0 minus plus 1 minus plus 2 and so on. Is it clear here? Right, that's enough for today. We finished chapter 17, the complex numbers. Now let us take an attendance. Any question? Can you enter the code, please?